and that functions are concave down when the first derivative is decreasing. But we know that increasing and decreasing are not synonymous with positive and negative. Increasing and decreasing refer to the derivative being positive or negative. So if we're talking about the first derivative being increasing, we have to talk about the second derivative being positive or negative. Okay, so on this one, so go ahead and you are going to take careful notes. At the end, I'm going to ask you some questions about how I got where I got, so make sure that you're ready to rationalize this so that we know that you know how to do it. Cool? All right, so the first derivative. So first off, since we just said it, what is the range of this function?
0 to 2 pi.
Okay. So as we go on, this is where our intervals are going to be bounded. Okay? So the first derivative of sine of x is cosine x. So set this equal to 0. And which one is cosine is 0 at
1
pi? Yeah?
0 and pi?
Yeah, pi over 2.
Probably.
Yeah, pi over 2. It's your unit circle.
So
Yep.
It's pi over, yeah.
so which one is which here? So
That's 0.
1. Oh wait, that's 1 0.
Oh, I thought we were talking about 3. Radian. Yeah. 1 to 0. 0, 1. Yeah. Well, yeah, in radian.
yes?
Yeah.
So then this is sine.
Yeah, and then. Wait, no, you're
Or we completely
x values cosine, y values sine, so it's going to be pi over 2, because then that's where your x value is equal to 0.
Cosine 0 is 1, and the cosine.
There. So that's going to be.
Cosine 1 is
at
0.
No, wait, it was, yeah.
so but this is at pi.
That's pi over 2. Because the unit circle is 2 pi radian. So that's pi over 2, yeah. 2 pi.
We good now?
Yeah.
So cosine is 0 at pi over 2.
Yeah.
Agreed?
Yep.
Shukai agreed? Say no. Say no now or forever hold your peace. That makes sense graphically, so if we want to test it, Shukai, graph it.
You know that shit. Or just do inverse cosine of 0.
Thank you. Spencer?
Oh,
Okay.
how can I forget
Yes?
about it? Yes.
Good. I'm glad we all want to feel good about this. We can all feel good. There are lots of ways to do this. So,
Oh.
x equals pi over 2. So this is our min or max, or our local extrema. All right, same sign analysis that we did yesterday for the first derivative, so pi over 2. So when x is less than pi over 2, like 0, cosine is positive. When x is greater than pi over 2, like pi,
Negative.
cosine is negative on this interval, right? So bounded also by 0 and 2 pi.
I have a question.
Yeah,
Wait.
we
In the
do
interval,
0
shouldn't we have more than one? 3
Yeah,
pi over 2?
3 pi over 2 as
Yeah.
well, no? Yeah, I was going to say.
Okay. So
And then it's going to switch again, because the...
it should be negative, and then it's going to be positive.
Yeah.
There we go.
Better? Okay, so our intervals, we are increasing from Now, this is something you're gonna have to ask Mrs. Leafhead about. Well, so since the range has the 0 included, I'm gonna include it in my interval too, but I'm not sure if that would change if it was not included.
Okay.
So that's something that you should clarify with Mrs. Leafhead on Monday. But since it's included here, I'm gonna include it in my interval range. So, it's increasing. It is decreasing. And then increasing again. So if it's increasing 2 pi over 2, decreasing after pi over 2, what does that tell us about pi over 2? Is that a min or a max? Increasing and then decreasing. Increasing.
Max.
A max.
It's a max.
So we have a local max at pi over 2, 1, yeah?
Yes.
And then at 3 pi over 2, it's decreasing and then increasing, so that is a Alright, so this is everything pre-concavity rule. So this is just defining local mins and maxes and intervals of increasing and decreasing. So now for the concavity rule, we need to take the second derivative. So just to remind us, our first derivative was cosine x. Our second derivative will be then negative sine x.
Yes.
Okay, so this is going to be 0 at 0 and 2 pi, correct?
Yes.
Yeah? Because even though, remember, if we're thinking graphically, the negative means that the sine function has reflected across. So our maximums are now minimums and our minimums are now maximums, but those 0 points stay the same because we haven't stretched or shrunk our function at all. So x is equal to, or the,
It's gonna be
at 0 and 2 pi, right?
pi.
And pi, thank you, Spencer. Okay. So then we're gonna do the same sign analysis. So our range is from 0 to pi to 2 pi, and it's actually important. Spencer's actually right. That's gonna be the only thing within our interval because 0 and 2 pi are at the end. So we don't need to look at before 0, and we're not gonna look at after 2 pi because those don't exist given the range that we were provided. So between 0 and 2 pi, if we are at pi over 2, sign has now flipped, so that's negative. We're looking at 3 pi over 2,
Positive.
sign has now flipped, right? Because it's a negative sine x, so now it's
Positive.
positive. So what this tells us is that on the interval from 0 to pi, x is concave down. From pi to 2 pi, x is concave up. So now let's actually see how this looks on our graph, the graph that we already know. So we graphed the sine function. So sine function is 0 at 0. And let's say this is pi, this is 2 pi. So we have our max at pi over 2, a min at 3 pi over 2, and then, oh, we must, how many intervals did we say for concave? Yeah, this is right. So we have 2 intervals. So we have concave up from, or we have concave down from 0 to pi,
Yeah.
and concave up from pi over 2.
Yep.
Trig functions are a good one to check it because you know so much about them graphically just because of how they are, that some of the flips and the reflections that happen naturally make a lot of sense. and help you do the concave up and down more easily. Okay, well, you guys knew how to do that problem better than I did, so I won't ask any questions about it. You guys did a great job. All right, so let's move, and when I look at my work, so what would we call pi here? What is the formal name for what pi is serving in terms of the function? Point of inflection. So let's go back, check our so this is leading us into that question. So is this a point of inflection? So a point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. So as Spencer said in our previous problem, x equals to pi would have been a point of inflection because that's where the sine graph changes from concave down to concave up. So we'll look at a quick example. So f of x equals, or f prime is going to be 3x squared. No plus c because there's no constant. Right, I'm going to skip just to see the point of inflection. The second derivative of this is going to be 6x. So 6x is equal to 0 at x is equal to 0. So that's going to be the inflection point. So that's going to be at 0, 0. Because if I plug that 0 back into the original function, that gives me 0. So then our same sign analysis applies. So we know that at this point, it's either going to be changing from concave down to concave up, or from concave up to concave down. And that kind of gives you a sense of what the function could look like, even if you're just looking at that point of inflection. Right? So we only have so many ways that you can go from concave up to concave down. Okay, so we would say that it is, now if we did our sign analysis from 0, if x is less than 0, this is going to be, 6x will be negative, positive, so it is on the interval from yes?
Yep.
Okay, great. Yes.
I was like doing the homework last night, and I was doing like 17, 19, and it's with like the point of inflections, and like the algebra and stuff would work out, but then when you went to graph it, like the graph wouldn't show like the point of inflection like at that point, but then the back of the book said like it was the point of inflection, so I was like, I didn't know what was going on.
Yeah, this is a clarification that so we're going to see that with an example that comes up a little bit later, Spencer. So that's a clarification that Mrs. Leith had made to me to make sure I made to you guys, which is that points of inflection have to be in the original domain. So did you restrict the range when you... Does that make sense?
Yeah, I see what you're saying, but I'm not sure if it would apply to these.
I'm not sure either. So let's put that, what problems were they?
It was like 17 and 19.
17 and 19?
Yeah.
So let's put those over here. Let's start with those tomorrow.
Okay.
And we'll see if what we learned today kind of resolves this issue.
Okay.
So we'll start with those tomorrow, make sure that we're all good about why that would be. That'll give me some chance to do some research too. Okay? All right. So let's go on to another example. So go ahead and do this right now on your own. So you are identifying mins and maxes, intervals of increasing and decreasing, points of inflection, and intervals of concavity, and I'll erase you on a whiteboard.